For this problem, we want to figure out what the pattern is and then start talking about the pattern. We want to describe the relationship between the number of triangles in the perimeter of the figure that is formed and represent the relationship using a table, words, an equation, and a graph. All four of those. So the first thing I recommend doing is just looking at the figure and seeing what's going on. What is going on as we move from the first instance to the next one and the next one and the next one? We're adding a triangle each time, okay? So if you think about that, remember that we're talking about variables here. In each figure, from one figure to the next, we are adding a triangle. So the number of triangles is changing, which means that the number of triangles is a variable. Okay? Now, is that the thing that we control or the thing that happens because of something else that we did? That's the thing we control. As we move from one figure to the next, we have to add a triangle. Okay? That's what we are doing. So the number of triangles is the independent variable. So I could actually write that down right now if I wanted to. Which letter goes with independent variable, x or y? X. So I could say x equals the number of triangles. It's not just triangles, it's the number of triangles. So now the rest of the problem says, what is the relationship between the number of triangles? Well, there's my variable x right there. And what? The perimeter. Is the perimeter constant here? Well, if I look at the first triangle, the perimeter is, add up all the sides, 10, right? If I look at the second figure, the perimeter is all the outside stuff. If I add all those together, I get what? 14. For the third figure, the perimeter is all the stuff on the outside. If I add all those together, I get what? 18. And for the fourth one, the perimeter still is everything on the outside. If I add all those together, I get what? 22. So what's happening each time I add a triangle? I'm adding 4, okay? Each triangle adds 4. So we can keep that in mind. Is the perimeter constant? Does the perimeter not change? Or does the perimeter change? It changes. And if something that changes in our problems is a variable. So that would be, if x is my number of triangles, then what? What's my other variable that I use? Y. And y would have to be the what? What are we talking about here? Perimeter. The two things that change in this problem are the number of triangles, that's what we control, and the perimeter. That's what happens because we added another triangle. Okay? So there's my two variables. So from this, I can now write an equation fairly easily. Fairly easily. The more practice you have with this, the easier writing the equation will become. The hard part is recognizing what the pattern is. Once you have the pattern down, you can write the equation. So we have to write words first, or not first, but let's write the words down. In words, what is happening as we go from figure to figure to figure? Well, where did we start? So we started with 10, right? So for each additional triangle, what do we do? Add 4 to the perimeter. Look, 10, 14, 18, 22. We're adding 4 each time. So add 4 to the perimeter. We happen to start with a perimeter of how much? 10, okay? So now from the words, I can write my equation fairly easily. My perimeter, which is what I'm looking for, is y. Equals. If I don't add any more triangles, I don't have to add 4. So what do I start with? My first figure, what's my perimeter? It's 10. So I have 10. The perimeter is 10 in my first figure. But as I continue, it says for each additional triangle, add 4 to the perimeter. So for each, we need to increase by 4. What does that mean? What are we going to do? So just plus 4? Is that it? That only gets me to 14. That doesn't get me to continue. 4x. For each, for every, per, things like that. Those give away that there's a variable on that number. So we have add 4 to the perimeter. For each additional triangle, add 4. So we're adding 4 for each. So that's where the 4x comes from. That's the equation. So words, we got them. Equation, we got it. Now we just got to come up with a table and graph. The table is just going to have my numbers in it that I came up with. So I have x, I have y, and in between I have my equation, 10 plus 4x. We're going to be doing lots of these in this class. 3-column table. Some people call them XY charts. But the middle shows the work. So we have 1 triangle, 2 triangles, 3 triangles, and 4 triangles. So I'm going to write 1, 2, 3, 4, because the x represents the number of triangles. Then I'm going to substitute in. On each one of these lines, I'm going to substitute in. So I write 10 plus 4, substitute in the 1 for x. Then 10 plus 4, substitute in the 2 for x. Then 10 plus 4, substitute in the 3. And then 10 plus 4, substitute the 4. Okay? I did all those at once so that you could see how that work shown is supposed to look. Now you just simplify this. And most of the time you can do these sorts of things in your head. 4 times 1 is what? 4. And then 4 plus 10 is 14. Then we have 18. And then we have 22. So actually our equation is giving us slightly wrong answers here. Then we have 26. So that's not quite what we wanted. And somebody earlier was telling me it's not 10. It's 6. Why is it 6? We don't want 10 here. We want 6. Why is that? Yeah. So I got to get rid of that 10 there. And then all of those 10s go away. It's actually 6. So if you think about this a little bit farther, I got ahead of myself, I guess, and I forgot. This should be a 6. If you look at the figures, the thing that doesn't change in these figures is right here. There's the 3 and the 3 for a total of 6. And then in the next figure, the 3 and the 3 is still there. And then in the next figure, the 3 and the 3 are still there. And the next one, the 3 and the 3 are still there. Those 3s are always there. There's always 2 of them, and they always add to be 6. So that means that 6 is always there in our equation. Then to get to the 10 that we need, we're going to add 4. How many 4s are in this figure? 1. How many 4s are in this figure? 2. How many 4s are in this figure? And in this figure, 4. Okay? So that's where the 4x is coming from. How many 4s are there? 1. How many 4s are there here? 2. How many 4s are there here? 3 of them. So now I have over here 6, 6, 6, and 6. And now 4 times 1 is 4 plus 6 is 10. 4 times 2 is 8 plus 6 is 14. 4 times 3 is 12 plus 6 is 18. And then 4 times 4 is 16 plus 6 is 22. Okay? That's why it's helpful. And I'll be honest, I did not intentionally make that mistake. I did get ahead of myself. But that's why it's helpful to make the table. Because as soon as I started making the table, I was like, wait a minute, my perimeters are supposed to be 10, 14, 18, 22. I'm off by 4. I'm 4 too high. So I must have done something wrong. I should have 6 sitting right here. Okay? So the more problems you do that are like this, the better off you're going to be because you will be able to recognize mistakes that you make. That being said, this is a great time to bring up the point that this does not go away. You need to know how to do these types of problems. You need to let your brain grow. Okay? We can't just rely on being able to do 4 times 5 anymore. That's not making your brain think. That's like automatic stuff. Let your brain think a little bit. It will grow. It will become used to this. And you will be able to come up with these answers. So now the last thing we need to do is come up with a graph. There's a bunch of stuff I have to do before I can even graph this. What do I need to do first? You got to figure out where the axes go. Where is the origin going to be here?
On the corner down.
Why can I put the origin here?
Because all that.
We don't have any negative numbers. That's right. There's never going to be a negative number of triangles. There's never going to be a negative perimeter. So I can put my origin in the lower left-hand corner. Notice that I've shown a little bit of a cross here, a little intersection. That's basically telling me that these negatives here don't matter. These negatives here don't matter either. All I care about is this quadrant. It's kind of like I zoomed in on this quadrant right here. The next thing I need to do is tell what is going on each axis. So for my horizontal axis here, what's that going to be? Yes, it is the x-axis, and we called x the number of triangles. So I'm putting number of triangles here. Which makes perimeter on my other axis. I still can't graph. I have my axes down, I have my labels for my axes down, but what I don't have is my scale. I have to make sure that I have a good scale here so that my graph actually shows what I want it to show. So, take a look at your x variable, 1, 2, 3, 4. Am I going to be able to fit all of those on this grid? Yes, so I can just go by a standard 1. So go by 1 there. Now if I look at y, I have 10, 14, 18, 22. There's only 14 lines on this grid. Will I fit all of my dots? No. So I need to go by 2s, which means each one of these lines represents 2 units. So up top, I'm going to write by 2. And then along the side, I'm going to label a couple of those numbers along the way to help me. So I'll go 2, 4, 6, 8, 10 here, and then 12, 14, 16, 18, 20 here, and that should be good enough. That just helps me so I don't have to count every single time. Now I'm ready to graph. I have my axes on there. I have labeled my axes. I have scales on there that are going to be good enough to show all my dots. Now I can draw all the dots. The ordered pairs for these dots come straight off the table. Here's an x coordinate, comma, a y coordinate. So I have the ordered pair 1, comma, 10. To get to 1, I go over to the right 1, and then I go up to 10, which is right there. And I put a dot. Then I have 2, comma, 14. So from the origin, I go over 2, and then I go up 14. Well, there's 10, and then 12, and then 14. What's my next ordered pair? 3, 18. So from the origin, I go over 1, 2, 3, and then I go up to 18. Well, there's 14, there's 16, there's 18. And my last ordered pair is what? 4, 22. So from the origin, I go over 1, 2, 3, 4, and then I go up to 22. So that's 20 right there. There's 22. That's your graph. Now the problem doesn't ask you this, but if I wanted to, could I draw a line on there that would go through all those dots? Yeah. Yes, I could. Okay. We are not going to. It doesn't say to. But pretty soon it will. Just not in this section. Okay, another problem that's very similar to the ones that we've been doing. The table shows the relationship between the number of photos you take and the amount of memory in megabytes left on your camera's phone. And they're actually telling you the photos you take is X and the memory left is Y. So they're giving you a little advantage there. You don't have to think about which variable is which. But I would rather you thought about it, so we'll talk about it too. And this is your camera's memory chip, so let's make that your camera phone, just to make it a little bit more relevant to you guys. And maybe we're doing like Snapchat here. Okay? Lots of Snapchat. Is a relationship a linear function? So now it's asking you, is it a linear function? We don't know until we take a look at the graph. Actually, we can figure it out if we look at the table, but in general, we're going to look at the graph. Then describe the relationship using words, an equation, and a graph. Okay, so we're Snapchatting. We got our phone out, and for some reason, we have this much memory, How many photos have we taken then? So that's like where we start. So on your phone, you got all your videos hanging out. You got all your music that you've downloaded off of iTunes crowding up your phone, and you're left with 512 megabytes for pictures. Is that a lot of memory? Not really, not in today's standard. So then I take a picture, what happens? What goes down? So the amount of memory I have left decreases, okay? So this is memory on my phone, or is it memory remaining on my phone, or is it the memory that I get on my phone? What is this? It's the memory remaining on your phone. So I'm going to actually write that down. Y equals memory remaining. And X equals what? The number of pictures, so pics, taken. You do want to write down your variables just so that you know what they are, okay? Now, I take a picture, and then I take a picture, and then I take a picture. I take my first picture, and how much memory have I lost? 3 megabytes. So that picture was 3 megabytes. And then I take another picture, and this time, like I'm Snapchatting, so this time I'm going to send it to like my brother or something. So this new picture cost me how much memory?
3 megabytes.
All right, and then that wasn't enough because I'm totally addicted to Snapchat, and I had to take another picture and send it to somebody else. And now I'm left with how much memory? How much memory am I losing per picture? Okay, so if I'm taking one picture and then another picture and then another picture, and I am losing the same amount each time, that actually is showing a linear relationship. So from the table right now, I could say, yes, this is a linear relationship. But the problem is actually asking me to graph it, and then from the graph show that it's a linear relationship. This is coming up. We'll be doing this pretty soon in this class, looking at tables without looking at a graph to say if it's linear or not. Okay, so we should probably come up with some words here. Describe the relationship using words, and then we'll come up with the equation, and then since they already gave us the table, we'll just make the graph. So how can I say in words what's going on? I like that. Let's stop there. For every picture that we take, what happens? So we lose 3 megabytes. So instead of we lose 3 megabytes, we decrease by. A good way to say that using our operations would be that we are going to minus or subtract. We subtract 3 megabytes from the remaining memory. Okay, so the words describe exactly what's going on in this situation. Now the question is, how do I write the equation? So if y is the memory remaining, then I can write y equals. If I haven't taken any pictures, then y equals what? Y is the memory remaining, that's right. So y is 512. So what is the equation that I'm going to write going to be? Y equals 512 minus 3. That's if I took one picture. This is now if I take a bunch of pictures. Any number of pictures, and now I know how much memory I have remaining. That's the equation. Okay? So now if I took one picture, 3 times 1 is 3. 512 minus 3 is 509. If I take 3 pictures, negative 3 times 3 is negative 9. 512 minus 9 is 503. So we are now getting what we're supposed to be getting. Always check. It doesn't take much time. Check it to make sure that it's right. If it's wrong, try to figure it out. I'm telling you, you will grow as an algebra student much faster if you really try at these problems. They will become not that difficult. Okay, so we have the words, we have the equation. They gave us the table to start with. So all we have to do now is graph it. How do I graph this? Okay, where are my axes going to go?
Because there's no negatives.
So yes, there are no negatives, so I'm going to put my axes here. Memory is on the y-axis. It's memory remaining. And then on the x-axis is number of photos, number of pictures taken. All those Snapchats. Okay, now what? Scale. So if I look at x, my horizontal axis, I got to go 0, 1, 2, 3. Do I have enough room for that?
Yep.
Yeah, so I can just go by 1. Okay. How about for y? One's with a break? What do you mean by a break? How do I show a broken graph? So like this? Is that what we're talking about? Sort of? Yeah, well you're right. Okay, so if you look at these numbers, 512 to 503, those numbers are really, really close together, but they're really far away from 0. So when something like that happens, it is possible to show all that. Like if I was to show 0 all the way up to 512, even if I change my scale, I'm still going to have a graph that goes from like the floor to the ceiling. Okay? And I don't want to do that. So what I'm going to do is I'm going to cut out all that wasted space from the floor to the ceiling and just leave the part that's important, the part that I care about. So I can still put 0 right there, but then I need to draw in a little break, and that's how I show a break on my axis. And then I'm going to put my 500 right there. Now from 500, I got to make it all the way to 512. So do we have enough lines to go by ones? 500, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have exactly 512 sitting right there if we do that. Okay? So now I can put by ones again. And then I'll mark a couple. We have 500. 1, 2, 3, 4. Here's 5. 505. And then 6, 7, 8, 9. Here's 510. All right, I have my axes on there. I have my labels on there. I have my scale on there. Am I ready to graph? Yep. Yeah. So we just start plotting points. We have 0, comma, 512. So here's 0, and then 512 is all the way up here. So I put a dot there. Then I have 1, comma, 509. So I go over from the origin, I go over 1 to the right, and then up to 509, which is right there. Then I have 2, comma, 506. So from the origin, I always go from the origin. I go over to the right 2, and then up to 506, which is right there. Then I have 3, comma, 503. So over 1, 2, 3, and then up to 503. Here is 500, 501, 502, 503. All right, now we have all of the stuff they asked for. We have to answer the question, is this a linear function?
Yeah.
How do I know it's a linear function for my graph? Because it looks like a line. If I were to take a ruler and line up my ruler, I would make a nice line right here. I'm not going to, but I can see how that would be a line. So the answer here, is this a linear relationship? Yes, it is linear. We have 2 more problems to do for this section. The first one says, is the relationship in the table below a linear function? So they're actually asking for a linear function this time. Describe the relationship using words, an equation, and a graph. Now this time there's no fun story. We're not Snapchatting. We're not doing anything exciting. They just give us some data. They tell us that the input and the output are sitting there. They're telling us that the input is X and the output is Y. Very boring problem. What should we do? I don't want to waste time making up a story. I just want to do the problem. Words? Okay. So in words, notice the pattern here. How much are we going up by with our inputs? 1 each time. What's happening to our outputs as we change? We're going up by 2. So, in words, so stop. For every one input, for every additional input, what happens? The outputs, what? Goes up by 2, adds 2, increase by 2. There's your words, okay? I made it a little bit more fancy than adds 2, but adds 2 is fine. As long as you get the words on there that make sense. So, describe using words we did. Didn't take long. See, that first one was tough, but now that we've done a few of these, you guys are starting to get faster at it. So, listen to my advice and try these problems and really think about it. Your brain will grow. Okay, now an equation. Y equals. What happens if I have no inputs? I'd have 0 inputs, but I get 8 outputs. So if I don't have any inputs, but I have 8 outputs, then what should I write? Y equals 8. Did I put anything into that equation? No. Did I get 8 outputs? Yes. But now, for every additional input, we have to increase the outputs by 2. So increase by 2 tells me I'm going to add 2x. Because for every additional input, we increase by 2x here. Now, does that give me all of the data that I have in that table? If I have 1 input, 1 times 2 is 2, 2 plus 8 is 10. If I have 3 inputs, 3 times 2 is 6, plus 8 is 14. Am I getting the right answers? Yeah. So that's the equation. Now we need a graph. So just like before, I need to figure out where my origin is going to be. No negatives again, so we can put that origin where we've been putting all the other origins. It's not always going to be like that. What will go on my horizontal axis? The inputs. Look, they even called the inputs x. So that's my x-axis. This is my number of inputs. The y-axis is going to be the number of outputs. Do I know what the inputs and outputs are? No, I don't. It doesn't matter. It could be baby chickens and chicken nuggets. Doesn't matter. That was pretty terrible of me. Okay, now what? We need a scale. So look at the inputs, look at the horizontal axis. Do we need to change our scale? No, so we can just go by ones. Look at the vertical axis, the outputs. Do I need to change my scale there?
Yeah.
Actually, I have 14 lines. I got to make it to 14. Do I need to change the scale? I actually don't. So I can go by ones here as well. All right, so we just need to plot those ordered pairs. By plot, I mean graph. We have 0, 8. So how do I graph 0, 8? So on the x-axis, we go to 0, which is right there. And then from there, we go up to 8. 1, 2, 3, 4, 5, 6, 7, there's 8. All right, 1, 10 is my next ordered pair. How do I graph 1, 10? So on the x-axis, I go to 1. And then from there, I go up to 10. There we are right there. What's my next ordered pair? Well, what's the next ordered pair, though? 2, 12. So I go over to 2, and then I go up to 12. You're always starting back at the origin. And what's my last ordered pair? 3, 14. So what do? From the origin over to 3, and then up to 14, and that's the very top. All right, so is the relationship in the table below a linear function? Yes, it is. How do I know it's linear? It looks like I could put a line on that thing. If I look at the table here, I'm changing by 1 each time. For my outputs, I'm changing by 2 each time, and that actually does signify a linear relationship. So the answer here to this question is yes, it's linear. One last problem. Does the set of ordered pairs listed here represent a linear function, yes or no? So I got some no's. Why not? Okay, yeah, so there's actually several ways to answer this problem. We're looking at these ordered pairs, and it's asking for a linear function. So if it's not a function, then it doesn't matter anymore. It's not even a linear function. Is this a function at all? How do I know if something's a function or not? No repeated x values. So I have, for my x coordinates, I have a 0, I have a 1, I have a 3, and then I have another 1. So this isn't even a function. So the answer is no. Now the explained part is the important part. I'm going to say no, it's not even a function at all because of repeated x values. So that's one way that you can say that it's not a linear function. What's another way? Something else you could do to decide if it's linear or not. You could graph it, yeah. So I don't have another grid. I'll just make a little grid right here. So I have 0, 2, which would be like right around there maybe. And then 1, 4, so here's 2, and then 3, 4. And then 3, 5. So 1, 2, 3, and then 5 is like right there. Am I making a line? No, it's not even close to a line. And then this last ordered pair right here, 1, 8, would be all the way up there. There's no way you can draw a line through all of those dots. Okay? So that would be another way that you could say, no, this is not a linear function. Clearly, it's not linear. Okay? You say it's not a function, that also means, no, it's not a linear function. And there are other ways as well. You could say it doesn't pass the vertical line test, therefore it's not a linear function. You could look at the table. You could make a table out of these values and say, well, we're changing by 1, and then we're changing by 2 here, and then whatever. Here we're changing by 2, and then we're not changing by 2, and then we're changing by a whole bunch. So it's all over the place. Like this table changes a nice number each time. 1, 1, 1, 1, 2, 2, 2, 2. That's a linear function. This, no way.